In my last series of lectures, we started to go through the kinematics of different situations involving rotations. Rotation about a fixed axis, and then a rolling object, that is an object that is rolling without slipping as it undergoes a rotation and a translation simultaneously. The rotation is about the center of mass of the object. Soon we'll begin to describe the dynamics of such situations, applying F equals ma to situations involving rotations to understand the cause of angular acceleration. However, prior to doing so, we need to do a little bit of mathematical background, and with this mathematical background, I will also formally take you through a little bit more of exactly what is meant by the right-hand rule. This mathematical background that we need is the second way in which we multiply vectors together. If you recall back from chapters 7 and 8, the first method of doing so is called the dot product. Now here for rotations, we need what is called the cross product. So let me take you through the basic mathematics of this specific type of vector multiplication, that is the cross product. This will, by the way, actually be a two-step process in doing so. For now, I'm going to take you through the cross product without the use of unit vectors. A little bit later on, I'll take you through the cross product when we do include descriptions of unit vectors. But for now, without unit vectors. Okay, let's say that I have two vectors, A and B, and they're related to each other geometrically. So right here we'll say is vector A, right here is vector B, and then to show the geometrical relationship between them, right here I'm going to go ahead and draw an angle like so, call it theta. Okay, now I'm going to specifically calculate what is called the cross product. When I do, I end up with another vector, which is going to be called, we'll say, vector C. So vector C is going to be equal to A cross B. Use the multiplication symbol here, don't use the dot symbol, and then we write this as A multiplied by B. You pronounce this as A cross B. Okay, now first of all, the vector C's magnitude. The vector C has a magnitude which by definition is equal to the following. We take the magnitude of A, multiply it by the magnitude of B, and then multiply it by the sine of the angle that is formed between the two vectors. Recall that the dot product is in terms of the cosine of the angle. This particular form of multiplication is the sine of the angle. Okay, now what exactly is being multiplied together here? Well, you can think of it a couple of different ways. So for example, let's say that I write the vector C as A times quantity B sine theta, like so. Okay, if I think of it like that, let me clean this up a little bit. Okay, if I think of it like that, then the following is being multiplied. So here is the A from before, here is the B like so, and then right here is the angle theta. And now what I'm going to do is take the vector B and break that into components. I'm going to break it into a component that is parallel to A, and then right here perpendicular to A, like so. And then this guy right here, this perpendicular component, this is the B sine theta. Recall that the B cosine theta is this quantity here. This then led us to the dot product. Essentially what we're doing is that instead of taking the parallel component, we're now using instead the perpendicular component. So we're taking the piece of B that is perpendicular to A and then multiplying it by A. Or alternatively, you can think of it like this. You can think of it as A sine theta multiplied by B. If you do, in this case, what we'll do is take the vector A and break that into components instead. Okay, so here's A, here's B, here's the angle theta, and now we'll take the vector A and break that into components. So I'll use a different color. Okay, right here is the parallel component. This would be A cosine theta. And then right here is the perpendicular component. This right here is A sine theta. So we're once again taking the piece of one vector, in this case the vector A that is perpendicular to the other vector, and then multiplying it by the other vector. However, you actually have already seen this description, for example, right here of the cross product before in geometry. Here's how you saw it in geometry. So let me write it as B times A sine theta. Specifically, what geometrical figure is this the area of? It's the area of a parallelogram. which what you saw in geometry in the following way. Okay, right here is a parallelogram like so. Okay, right here is A, here is B, like so, and then A sine theta is right here, like so, where this is the angle theta. So A sine theta times B, if you recall that, then gives you the area of a parallelogram. So ultimately, when calculating the cross product, if you want to get really nitty-gritty into the math, you're finding the area of a parallelogram that is formed by the two vectors A and B. However, the vector C also has a direction associated with it. Recall that this wasn't the case for the dot product. The dot product always gave you a scalar quantity. However, in this case with the cross product, we do in fact have a vector quantity. That vector quantity is the direction associated, for example, with the vector C. How do we end up with the direction? Okay, let me jump back up to the top board to illustrate. In order to get the direction associated with the vector C, this is where now specifically we use the right-hand rule. So here's then how you use the right-hand rule. Do this yourself as you watch this video. Take the fingers in your right hand and you point them in the direction of the first vector A. And then what you do is you curl like so into the direction of the second vector B. The direction that your thumb points, that is then therefore the direction of the vector C. So if I go A cross B like so on this diagram, this then means that the vector C points into the board. So right here, as you saw in a previous video, is the symbol that we use to describe into the board, and then therefore the vector C points into the board like so. Okay, one other thing about this, in terms of the basics of the cross product, is that I could have, if I wanted to, had just as easily chose the angle in the following way. Let's say that I still have A and B oriented as before, but now let's say that I talk about this as the angle between the two vectors. This angle here, in terms of the original angle theta on the top board, is 2 pi minus theta. And now let's say that I say that C is equal to A cross B once again. Initially, it looks like I'm contradicting myself using the right-hand rule in the following way. Watch this. So I take the fingers in my right hand and I point them in the direction of A. And then I curl them like so in the direction of B. And then all of a sudden my thumb points onto the board. It looks like I violate what I drew on the top board when I had A cross B into the board like so. But watch this. Let's now go ahead and find the magnitude of C. The magnitude of C is going to be AB times the sine of this angle, 2 pi minus theta. Do you see a trig identity there? It's specifically the subtraction identity for sine. So watch what happens when I use the subtraction identity for sine. So sine of the first angle times cosine of the second, and then minus cosine of the first angle times sine of the second. Like so. And then let's go ahead and simplify the brackets here. So sine of 2 pi is 0, cosine of 2 pi is 1. And then after you do the math here, you end up with negative AB sine theta. What do you suppose the negative sign does when I go A cross B like so? It reverses the direction of my thumb back into the board, exactly as it should be, for example, on the top board when I originally did A cross B like so. So there actually is no contradiction because of this negative sign. So this negative sign reverses the direction back into the board. So then therefore the direction of the vector C is into the board regardless of which angle you choose. However, usually, just of course to make the situation simple and straightforward, we usually choose the angle as the angle that is less than 180 degrees. Okay, so this is the basics of the cross product without unit vectors. We'll get to that later. However, at this point, the mathematics that you saw here is enough to begin dynamics associated with rotations.